Hello everybody. Here are some ducks who are super excited to learn about ultrafiltration between the glomerulus and the Bowman's capsule. Okay, so urine formation is split into two stages: ultrafiltration and selective reabsorption. We are going to talk just about this first part about ultrafiltration. Ultrafiltration is essentially squeezing out everything that's in the blood that's small enough to get out. So the blood travels in through the afferent arteriole, and then it travels into all these little blood vessels on these little tiny capillaries. And then when it gets there, everything in that blood that can be squeezed out to form a filtrate in the Bowman's capsule. So remember, the glomerulus is like a big ball of string, a big ball of capillaries inside what is essentially a bowl. So the Bowman's capsule is like a bowl, and that bowl is going to capture all the stuff that's squeezed out. So it's going to capture all the filtrate. So try and just visualize that. Try and imagine like a sponge in a bowl. When you squeeze that sponge, all of the solution in it comes out. That's exactly what's happening between the glomerulus and the Bowman's capsule in a kidney. So why are we doing this? Well, because we're doing it because there's stuff in our blood that we don't want to be there. Maybe there's excess water, maybe there's excess salts, maybe there are toxins in there like urea and uric acid, for instance. We want to get rid of those. Maybe we want to get rid of, we'll lose some hormones, for instance. But we don't want to lose all of it. And the kidney's kind of an odd one. Like, you can imagine if you were like, right, I'm going to design a kidney, I want to get rid of some stuff. I'd have a little conveyor belt of everything going past, and as it went past, I would take out the stuff that I wanted to get rid of. But it doesn't do it like that at all. What it does is it gets rid of everything, and then it takes back all the stuff it wants to keep. So it sort of has this extra step. So we ultrafiltrate, we squeeze everything out, and then we take back what we want to keep. So let's think about all the stuff that we're going to take out of the bloodstream. Just take a minute to have a look at this lovely diagram. So here we've got the blood coming in. So we had the renal artery, and then the renal artery split up into arterioles. Here we've got the afferent arterioles. The blood comes in here. Take a minute to look at the difference between the afferent arteriole and the efferent arteriole. So can you see that the lumen of the afferent arteriole is wider than the lumen of the efferent arteriole? This is really important. Blood is coming in via the afferent arteriole, and that blood, as it travels along, is then going to come in here, and it's going to be in a smaller area. If you have the same volume of blood in a smaller area, what happens to the pressure? The pressure increases. So the difference in diameter of the lumens of the afferent and efferent arteriole creates high pressure. That's what puts the blood in the glomerulus under high pressure, and why everything gets squeezed out. So then as the blood travels into the glomerulus, everything gets squeezed out and forms this glomerular filtrate. And so we get all this filtrate formed here, and then the filtrate is going to travel down the proximal convoluted tubule, and we'll talk about that later. This is an important diagram, I think, for being able to visualize what's going on. So let's talk through the process. We've already talked about the fact that ultrafiltration occurs between the glomerulus and the Bowman's capsule. Sometimes the Bowman's capsule is referred to as the renal capsule. Just means the same thing. This word renal, you'll just come across a lot whenever you talk about the kidney. Renal artery, renal vein, renal pyramids. It's just a word that is associated with the kidneys, so don't worry about that one too much. So small molecules that are small enough to be squeezed out form the glomerular filtrate. So what molecules are actually small enough? Any molecule which is small and soluble and has a relative molecular mass of less than around 68,000. So an RMM, a relative molecular mass of less than approximately 68,000. Now, when I tell you this number, I need you to know that, it's not like a cut-off line, like 68,001, that can't get through. It's, there's variation, and not just that. Some textbooks will say like 69,000, some textbooks will say like 70,000. It's around that number, so don't stress out too much about that one. Once they're squeezed out, together that forms the filtrate. But what are we actually referring to? What are these small soluble molecules that are going to get squeezed out? Well, obviously water, salts, urea, hormones, amino acids, glucose, some vitamins and other mineral ions, and in addition to that, a few other things that we'll mention later, like some other excretory waste products like uric acid. So all these things get squeezed out and they basically form a solution that we call the glomerular filtrate. So what doesn't leave? Well, red blood cells and white blood cells obviously don't leave because they're massive. And in addition, your blood contains large insoluble proteins. So a couple of examples that I've just put here are antibodies. These are an obvious large protein. And albumin is another large protein in your blood. So the function of albumin is to keep the water potential of the blood low. So if you think about as blood is moving through your body, if it had a high water potential, then the water would just leak out of the blood vessels and it would go into all your tissues. So the albumin generates a lower water potential and therefore it holds fluid in the blood. So that's actually going to be a little bit important later on, so we're going to think about that a little bit later. So we allow out small soluble molecules and we don't allow out large proteins. So things with a relative molecular mass of more than about 68,000, and we don't let out blood cells, red blood cells and white blood cells. That's all pretty straightforward, right? But why is this stuff actually squeezed out? Why does it leave? Why doesn't it just stay in there and carry on moving? That doesn't happen in other organs of your body. You don't squeeze everything out of your blood. Well, we already mentioned one thing. The blood enters the glomerulus at very high pressure. And the first reason is that blood enters the kidney almost directly from the heart. The renal artery branches off from the aorta, and we know that blood is travelling at very high pressure through the aorta. So that high pressure hasn't really been lost yet. So that's the first reason. The second reason is the lumen of the efferent arteriole is smaller than the lumen of the afferent arteriole. This means that blood is being squeezed into a smaller space. This generates a high hydrostatic pressure that forces substances through the walls of the glomerulus and out into the Bowman's capsule. Okay, so in order to allow some things out and not others, we must have some kind of net. We must have some kind of barrier that prevents the movement of some stuff out of the capillary but not others. In fact, your glomerular wall has a complex set of nets. It has 3 layers. So if the first layer doesn't catch it, the second layer will. If the second layer doesn't catch it, the third layer will. So I just wanted to show you this rather beautiful scanning electron micrograph image of a capillary of the glomerulus. So this is the capillary, right, of the glomerulus. You're looking at it here in this 3-dimensional image. But what's been false coloured here is a single cell that has wrapped itself around the capillary. Can you see how this cell has these long extensions, these elongations? These cells are called podocytes. Site obviously meaning cell, and pod meaning feet cells. Look at all these little toes peeling off our podocyte. These cells, these podocytes, they wrap themselves around the glomerulus. So they form a layer of filtration. So if we just think about this one cell, can you see how this other cell sort of like all intertwined with it? See, it's quite hard to show the gaps. But the way that these cells are intertwined creates a little gap. And it's through this gap that very small things can travel. So we're going to talk about this layer in just a minute, but I just thought this was worth looking at so you could get a sort of visual image of what we're talking about. So the podocytes, they wrap themselves both around the capillary and they intertwine with each other. And they create a little gap through which very small things can travel. And hopefully you can see that all the way around. Can you see this is one arm, an extension of a podocyte cell, and then here's another podocyte cell, and then there's a little gap between them through which very small soluble molecules might be able to squeeze through. The same here. There's one podocyte extension, here's another cell, and here's the gap through which small soluble things can squeeze through. Okay, so let's talk about the layers of filtration. I think this is a rather fabulous diagram for showing you it because it shows you it from different perspectives. So if we imagine it holistically over on this one, so we can see, and then over in here we can see the whole thing. So here we've got the capillary, right? Here's the capillary, and we know that the walls of the capillary are called endothelial cells. So capillaries are 1 cell thick, and the walls of capillaries are endothelial cells. And can you see how you've got these little gaps, these little holes between the cells? These little circular pores between the endothelial cells are called fenestrations. It's a nice word. It's from the French, fenestra, window. Little windows out of the capillaries. It should really be door, shouldn't it? But it's not, it's fenestra. Have you ever heard of that word defenestration? It's like an English word. Do you know that word, defenestration? I don't know why this word exists. Defenestration essentially means to throw somebody out of the window. I don't know if historically we were throwing so many people out of windows that we had to like create a word for it, but there you go. Anyway, so small soluble things can come through these little pores. So that's the first layer of filtration, is the endothelial walls. And that's exactly what you're seeing on this big diagram here. You've got your red blood cells. They're too big to fit through the pores, the fenestrations here, and these are the endothelial cells, you see. Then there's a second layer. Can you see here this sort of brown thing here? This is wrapped around the capillary wall. So this is connective tissue. It basically, if you were to look at this in way more detail, it looks like a meshwork like this, all wrapped around each other. So it's a fibrous meshwork, and it's made up mostly of collagen and glycoproteins. So that's sort of there. You can't see that on this diagram here. And then wrapped around the capillaries, like we talked about at the very beginning, you've got your podocytes. Podocyte, foot cell. And the gaps between the podocytes is the third layer of filtration. That's exactly what you're seeing here in this diagram. So if the stuff fits through this one, and then it has to get through the connective tissue, then it has to get through the gaps in the podocytes. And then if it gets through each of those layers, it pops out here in the glomerulus, where it becomes part of the glomerular filtrate. So let's just recap those key ideas that we've discussed. What are the 3 layers of filtration between the glomerulus and the Bowman's capsule? The first is the endothelium of the capillary, which has more gaps than usual. We talked about those fenestrations, those pores between the cells. The second is the connective tissue. This can sometimes be referred to as the basement membrane, which is basically a network of collagen and glycoproteins, and these act like a filter to prevent large protein molecules and blood cells from being able to pass through. And then finally, the inner wall of the Bowman's capsule, these podocyte cells. And it's the gaps between the podocyte cells that allow the molecules to pass through. So I just wanted to talk to you for a second about this term, glomerular filtrate rate. This is the rate at which fluid passes from the glomerular capillaries into the renal capsule. In humans, this is about 125 centimeters cubed per minute. That is huge. That means we are sending about 125 centimeters cubed per minute of filtrate into our kidneys. We do not pee out 125 centimeters cubed per minute of urine. Nowhere near that. So clearly, almost all of it is reabsorbed. Nearly 99% of everything we squeeze out is reabsorbed back into our bloodstream. And that is the next thing that you are going to be learning about. But there's just one more key concept that we need to go through before we finish up today. So, we've already talked about this generation of high hydrostatic pressure, and that this causes molecules to pass into the Bowman's capsule from, I've spelled from wrong, which was rather depressing, from the glomerulus, but the water potential gradient acts in the opposite direction. So let's just think about that for a minute. So let's just say here's our capillary, here's our glomerulus, okay, and here down the bottom is our Bowman's capsule. And we know that we generate this high hydrostatic pressure. So we've got a hydrostatic pressure gradient. And we know this gradient is generated by, first of all, the fact that the lumen of the efferent arteriole is smaller than the lumen of the afferent arteriole, and also that the renal artery comes directly off the aorta. So you've still got the high pressure of the blood from the contraction of the left ventricle. So those two things generate this high hydrostatic pressure. However, we have a smaller pressure acting in the opposite direction. This is the water potential gradient. So why is this here? Well, it is here because of the presence of plasma proteins. So the plasma proteins that are here in the capillaries, they're too large to go out, but they lower the blood's water potential. Therefore, what we have is a situation where there are forces acting in both directions. The hydrostatic pressure gradient acting out of the glomerulus and the water potential gradient acting into the glomerulus. However, the hydrostatic gradient generates a higher pressure, and therefore net movement is from the glomerulus to the Bowman's capsule. So if somebody was to have fewer plasma proteins, that would affect how blood was ultrafiltrated out of the kidneys. So if you had fewer plasma proteins, you would have less of a water potential gradient, and therefore overall there would be greater net movement out of the glomerulus and into the Bowman's capsule. So that's just worth considering, because think about how in exam questions we often get asked, oh well, what if this happened, what if this happened, and so on. Just one more thing before you head off, because we've learned all the key concepts now. Just one more thing. So this is a light micrograph image, and I think that this is a good one to look at because sometimes it can be a slightly odd angle for us to get our head around. So here we've got the lumen of the glomerular capillaries. This is all lumen. And then we've got the endothelium. So we've got the cells lining our capillary. Here's a cell, here's a cell. We've got the little gaps between them, the fenestrations. And then this is our basement membrane, our glycogen and glycoprotein. And then you've got all this weird stuff over here. It looks like the sort of loads of little bits, loads of tiny cells. But actually, if you just imagine it's been cut, all these podocytes are probably part of one or two podocytes. Sorry, all these extensions, I meant to say, are probably part of one or two podocytes. It's just the way that it's been cut. Okay, so here are the extensions of the cells. And then this is the cell body. Okay, lovely. And then we can see some other lovely intracellular organelles here. So I think this is a really nice one to have a look at to get our head around sort of how the way a specimen is cut can impact what it looks like. So lots of key information that we have covered here. We have looked at what glomerular filtrate is made of, why glomerular filtrate is pushed out, and what causes only small soluble molecules to be moved out. So, well done for listening to all of that, and I will speak to you soon.